Well, today we will begin the next third of the course, which, or greater part of the third, which concerns magnetism. I think that it's been pretty rough going so far, I think, because we went so fast, and a lot of these ideas are new and different. But the nice thing about this section on magnetism is kind of a reprise of what went on with electricity. So if you didn't get electricity the first time around, I don't feel quite comfortable with it. I think the second time around, it will look a lot more familiar, I hope, and it should solidify the electricity part, and you'll learn something about magnetism as well. Now, magnetism and electricity are related, but they are different. Now, the outline of the chapter, as I see it, there's a basic idea that the magnets, unlike electric charge, where you can isolate a single electron or a single proton, and you can have a single source of electrical influence, with magnets, you can't do that. So far, we've never been able to isolate a single north pole or a single south pole. There are some theories that talk about it, they're called magnetic monopoles, but we always get magnets as dipoles. That is, you always get a north and a south. And we'll see how we handle that. Then, what the big discovery will be in section 2, that although we've known about magnets for a long time, thousands of years, permanent magnets that act and repel and attract each other, the great discovery was that electric currents can act like magnets. That was a big discovery. That was a civilization-changing discovery by the human race. So once electric currents are magnets, although originally you had the effect of magnetic poles of one material on another, sort of like, you see, one material on another, this is what we were familiar with, this kind of thing. But now we could replace one of those objects with an electric current. So an electric current acts as a magnet. The current will attract a pole, or a pole will attract a current, or two currents can attract each other because now they're both magnets, or they can repel. So that's what we'll see. And then we're going to try to formulate how you treat this new field, this new process, magnetism, and you'll see that it's very analogous to how we did both gravity and electricity. Magnetism is handled the same way. In other words, we had a good pattern of handling gravity and electricity, so we follow the same pattern in handling the magnetic effects, as I'll explain. And then we're going to do the categories of magnetic materials, which I mentioned briefly, and again, you will see a great parallel idea between what I talk about, the different kinds of electric materials. We had dielectrics, we had paraelectrics, where you had isolated dipoles, like in water, and then we had ferroelectrics, something much less familiar, where the dipoles line up and you get a very large macroscopic electric dipole. The same kind of thing goes on, little variations, with magnetic materials. You'll see we have diamagnetics, paramagnetics, ferromagnetics. And so there's this beautiful pattern that I'm trying to emphasize to you, because it's hard to remember isolated facts, but a whole pattern, I think, should be much clearer and satisfying. Okay, now I have this little joke, where this lady says she can't lose weight because the fillings in her teeth, the metal, attracts her to the refrigerator magnets, and so she can't stay away from the refrigerator. Well, that is not a good excuse, because in fact, most metals are not magnetic. So don't confuse the idea this thing is metallic, that it's going to be magnetic. In fact, most metals, like copper, gold, aluminum, silver, are not magnetic. We have a few special things, and then also we have a lot of magnets that are not metallic. Some of our strongest magnets, I would venture to say this is not a very good electrical conductor. And some of the magnets you put on your refrigerator door are probably not metallic magnets. They might be called ferrites. They're actually insulators. What makes a magnet magnetic is that the atoms inside have magnetic moments. They are little dipoles. And in a ferromagnet, these dipoles, by some means, are able to line each other up, and you get a very strong cooperative magnetic effect. But you don't need to be a conductor to do that. In fact, the strongest ones, I think, are not conducting. So don't get confused between metallic and magnetic. They are distinct properties. You can have one without the other. Okay, so then let's just look at things that are very familiar to you, because you played with magnets, I'm sure, as a kid. The first thing that people noticed was that some materials, if you just hung certain rocks on a string, they would tend to orient in certain directions. This is the idea of a compass needle. And in this case, we finally figured out, James and I, that they've painted these magnets with black is north. Okay, to remind me. We had a little question about which was which. So it turns out that even if I try to turn this thing, I displace it, it will tend to restore itself. It's wobbly, but it goes. Okay, tends to point north. A great idea that we attribute to a man by the name of William Gilbert was that the fact that this is happening, and you knew that other objects, if you took another rock, similarly with the black side, I could push that black side away with this black side. So he got the idea that the fact that this magnet picks up an orientation in the Earth, with respect to the Earth, say the way the sun was moving, it would take a certain position, suggests that the Earth must be a magnet. Now, that may seem very obvious to you, but apparently at the time it was a very big idea. In fact, one of the great physicists, Galileo, had great respect for Gilbert for noticing that, and just that idea that the Earth is a magnet, because it helps align these smaller magnets with respect to it. Okay, now, here's another case, like we had before, of two objects interacting seemingly without touching each other. So it's a non-contact force, another one of these mysterious, wonderful things. And in this case, there seem to be, again, two types. Because if I point this end, now I'm attracting, this white is attracting the black. And if I go over here, it will tend to go toward it. So obviously this guy's stronger than the Earth's field at this point. So the white is attracting its opposite number. Okay, so that's a basic fact that, now I wanted to make this analogy, how we treated this thing. First, fortunately, the first thing the physicists dealt with was gravity, and it turns out to be the simplest case. Newton finally understood that what was going on was that we had the Earth, which is a big mass, and we have other little things like his apple, which is attracted to the Earth. So there's a force between these things. The force acting on the apple accelerates the apple. It's the same force hardly accelerates the Earth because Earth is so huge. Okay, but there is a force here between two objects. And Newton finally was able to say, okay, I will quantify that. I'll say that it's proportional to the mass of one of the objects and the mass of the other of the objects, and inversely as the square of the distance. And that is between every two masses in the universe. In other words, this big mass is composed of little masses. but this guy is attracted to every one of these. And we saw in some cases you can simplify this, say in a solid sphere, you can simplify it down to the masses at the center. So it could be simple, but in principle, it's very complicated because this little mass here is attracted to all the masses in the universe by this law. Of course, as you get far enough away, it gets pretty weak force. Then the physicists, to make life easy for them but harder for us, they break that down into two pieces, g m over r squared times m. And we call this the gravitational field. So once we know what this big object creates around it, actually kind of a force field, the gravitational field, then we can put our little mass in here, and it will feel an inward going force. So that's the trick we play. Namely, we break it down into a source, which I less gracefully call the pusher, and the thing that's acted on, for lack of a better word, the pushy. And we break it down such that we develop a field around this object, and we find the field produced by the source, in this case, a mass, and it acts upon this. We did a similar thing with electricity, the electric field. We found that if you have a Q and a little q, same thing. The force between 1 and 2, the force of 1 acting on 2, say, is, again, some constant, Q. At the risk of boring you, I'll go through it again. And again, to make life doable, we break it down into the field due to Q1 over r squared. That's the field we call the electric field. And we have the, once we have that, we can then put our little charge in an electric field, and we get the forces acting. That's the process we did. Now, the complication set in here that it turned out, to each stage it turned out there's a little extra complication. That's why I think we're very lucky that we started out with this one, because it's the simplest thing. The forces are always attractive. Here we found that the Qs were both positive and negative. So you could get, as I say, if the charge were positive, then the field would go out. And if the charge were negative, then somehow the field would go in. And the forces, if on a plus charge, would put you in to a negative, or if you were an opposite sign. So that's the complication that's set in with here. See, unlike this, where everything is positive, this can be plus or minus, and that could be plus or minus. So that's, but fortunately, at least they were radial. Now we're going to go to magnetism, and things are going to get one step more complicated. We're going to have all of this complication, namely two sorts, right? We have our north and our south, the plus and minus. But what's going to be complicated is that it's going to depend on the motion of the charges. Boo. It's going to be complicated. And also, instead of things going simply radially, you're going to have to start using, this is going this way, that's going that way, the third thing is going that way. Oy vey. It's really not charming. But that's the way nature did it. What can we do? But at least we understand it now, which is pretty good. Well, yeah, we sort of understand it, but at least we can deal with it at best. So there is this other demo that is very kind of cute, and that is that to prove that there's always a north and a south. We can take something that is what's called a soft magnet. It itself is not magnetized. In fact, it's attracted to this because this is magnetized. So what's happening is that this guy is magnetizing this one, and so they're attracted. But now I can do something else. I can magnetize him. Let's see if I can do that. This is, okay, yeah. Let's see if I've achieved it. Oops, see, that's why I should put this in here. See, I've really magnetized. Now he's a pretty good magnet. Can you make this guy crazy? And then, see, before he didn't do that. Okay, so now the question is, well, suppose this is a north and this is a south. Why don't I just break it in half and isolate the north? Oh, I just want to hurt my hand, so let me do this. Oh, it's not so easy. Doesn't break so easily. Well, maybe I have to work. I don't know if I'm ruining the magnetism by this. Oh, dear. Maybe take stronger hands than mine. Oh, that's nasty. I probably need a saw or something. Let me stop groping. Maybe we'll try later when we have some time, if we have time. But the point would be that even if I broke this, what's going to happen is that if this was a north, a south would appear on the broken piece. And if this was a south, a north would appear on this broken piece. So no matter what I do, I can't pull apart the north and the south. And later on, we see the explanation of magnetism. And after I get some more training in the gym, we will break this and try it. Okay, that's a cute one. But anyhow, one other thing I want to say. When we speak of this as being a north pole, the black one, what we really mean is a north-seeking pole. The fact that it's pointing, it's pointing actually, we're trying to figure it out, toward the north. So if we're here on Berkeley, let's say we're on the west coast, this north pole is pointing toward the geographic north pole. Well, we know north poles attract south poles. So it must be that the magnetic pole here must be a south pole because norths attract souths. So when they speak of the north pole, they mean the north geographic pole, but it really is a south magnetic pole. That's a little, I don't know if that's a trick question anybody might ask you, but maybe a trivia question somewhere. But and the way we describe these things is that, like with electricity, remember we said that the plus will be lines emanating from it. We just did this arbitrarily. All we know is that the lines go from one to the other. What direction it is, we make a convention. We could have just as easily drawn it this way. Well, we make the convention that the lines leave the plus and go to the minus. We make the same convention with a bar magnet. We're going to say that the north, south, like if you put filings around here, as you sometimes see the picture, well, it doesn't really tell you which way anything is going. So we just make a convention, and we'll stick to this, and we'll use it a lot. And that is that in the dipole, the lines of magnetic field, which we'll call B, the vector, emanate from the north pole, just as they sort of emanate from the plus up here, and they go down into the south pole. So on this argument, what the Earth is as Mr. Gilbert pointed out, there's a north magnetic pole here, but it's at the south geographic pole. The lines come out of here, and you'll notice that the compass needle lines up with this compass needle has lined up with the the Earth's magnetic field at that point, but you have to take the north magnetic pole at the south geographic pole. That's just a little sideline, I think. Okay, so sorry about the failure there. That's tough stuff to break. So this is the conclusion. If you put these little filings near a bar magnet like that, you will see the filings form a shape. We're just going to say that the north-seeking pole is the one from which lines emanate, and that's just a convention. And the truth is, of course, that we can't separate the north and the south, but we could get a little handle on it by making, say, a very long, thin magnetic rod, such that the north being up here and the south being down here, they're pretty far apart. So if you go near the north end, you pretty much see mostly the north, and you go near the south end, see mostly the south. So you can sort of isolate it, but you really can't perfectly isolate the two. Okay, and then what one finds is that if you did that experiment with a long rod and take another long rod and have a north and a north, you'd find that, like with point charges, the norths repel each other with a force that goes down as 1 over the square of the distance. So we're going to get something like this between these like poles. Okay. Now, I just put this another kind of funny thing. I once bought a lint remover, and they claim that there's a magnetic action. It's not magnetic action, right? This is electrostatic, because when you rub this, you build up a little charge, and it picks up the lint off your clothing, so it's not magnetic. But people confuse these things. Just because there's an attraction, that doesn't mean it's magnetic. We know that you can electrostatic. I meant to bring that in. It's a nice brush. Okay, so here we have this. Now, people knew about this, as I say, for thousands of years, and if you charged up something like one of those pitch balls or these styrofoam balls with electricity and you brought it near there, you wouldn't get a major reaction. You know, there's always a little dielectric reaction and so on, but basically static electric charges never affected magnetism. Then came around the year 1800, in the late 1790s, when they developed batteries, you know, by having metal and acid, metal, metal. They finally figured out how to generate electricity in a convenient way, and people started experimenting with electricity in a controlled fashion, not just rubbing things and hoping for the best. And so we knew that, you know, static charges attract other static charges or repel them, and we know that permanent magnets affect other permanent magnets, but there was no idea that one electricity could affect magnetism. But then, in 1820, a man by the name of Hans Christian Ørsted did this experiment. The lore is that he was just making a demonstration for some people, demonstrating the effect of charges, currents, and he had a battery, and he just passed some current, but for some lucky stroke, he had a compass needle near the table. And when he passed the current, the compass needles moved. The other way, let's see if this guy will settle down a bit. You just witnessed a thing that's changed civilization. Literally, literally. Because think of what this means. For example, suppose I want to send a signal from Berkeley to Oakland. The old days, you write a little message, I would get on a horse and ride. Instead, you could run a wire from Berkeley to Oakland. You could have a compass needle in Oakland. You could throw the switch, and you'd send your message. You could go click, click, you know, dot dash, dot dash. In fact, that's called a telegraph. And in fact, we have Telegraph Avenue. There was a telegraph line from Berkeley to Oakland with a wire on it, where somebody could go in Berkeley could go like this and send messages instantaneously, virtually, between two places. That's a revolutionary thing. So that was 1820. The other thing that you might be able to do, see the thing is going? Now, at one point, the needle may be attracted to the wire in one sense, but if you reverse it and it swings back, then if you could somehow get it to attract again, you might get the thing, if you go clever, you might get the thing to keep turning. So you've got the beginnings of a motor. Because if I could do that, I could attach that turning thingy to a cart, and I have an electric vehicle. So I might play games like get it going, and then get it going, and get it going, and get it going. This guy's doing well here. See, I made a motor, if you can do that right. Just attach that to a car, and you've got a motor. Or an electric drill, or electric toothbrush, which all we've been yearning for all these centuries. So that was the experiment. So simple. But it changed the world, because you could then transmit information. In fact, you could transfer energy, because you could make a motor move, or you could grind some corn, or whatever you wanted to do with this rotating thing. So that's Ørsted's experiment. Amazingly, Ørsted's name is not mentioned in your book. I don't know why. The man changed the world. In fact, he wrote a little pamphlet apparently in 1820, and it circulated around Europe. Caused a sensation, obviously, I mean, because the implications are tremendous. And particularly, the French were very well positioned, because they're very intellectually high level in the 1820s. It was after the French Revolution, after Napoleon, but they somehow had recovered from all that, and there were some very brilliant men around who could jump on this idea. And so a lot of the developments that happened were in France in the first year. One of these was by the man by the name of Ampere, whose name you've heard before because we named current in honor of him. And he said, well, if I pass current through this wire and it affects a magnet, this wire must be a magnet.